So I think that it is 4 o'clock and we're ready to start. You are already online. At some point, the Mandana shooting would be the second one after you. So first of all, good afternoon, everyone. Welcome to the Cloud Seminar Series. I think I can state that for the first time ever, we have 3 presentations. One session, and not only that, but I promise that we're finishing by 5 o'clock. Right? Yeah. The first speaker is Pooja Tambulkar. He is going to be talking about the automated parking. Pooja is a PhD student who is now past the qualifying exam and developing a plan for her dissertation research. She'll tell you a little bit about some of the things. So, all yours.
Good afternoon, everyone. My name is Pooja Tambulkar, and I'm going to present a brief introduction on automated functions. Automated functions in vehicles have become more and more present, and while a fully automated car is for the masses is still in a distant future, there are functions like adaptive cruise control, lane centering, stability control are becoming more and more normal. One of the reasons why this is happening is the improvement in sensitive technologies and capabilities, while the cost of sensors is also reducing quite significantly. So a same sensor hardware set can be used for multiple features. We can have multiple level 2 and level 3 features using the same hardware. One of the features which which we can develop because of this improvement in sensor technology is automated parking on self-parking lanes. This technology is not new, and this still exists in production level vehicles, but the technology today is not mature enough and not necessarily satisfying to the consumer point. In the future, although this can be an attractive add-on feature for people who find parking in general difficult, and this would be given as an add-on feature. There are a couple of sensor limitations in the production vehicles. This feature uses ultrasonic and camera vision technologies. Currently, ultrasonic sensors require unified objects, so it requires a car or a curb to detect a parking spot. Also, it has limited range, so it reduces the reliability when the vehicle is moving at a faster rate at the parking lot or is further away from the parking vehicles. The system still fails to detect that empty parking spot. With vision systems, the vision systems are sensitive to weather conditions, weather and light conditions. So if the weather is not optimal or it's an indoor parking space, it becomes harder for the system to detect a parking spot. The parking systems today are still a level 3 feature and still require the driver to be in control or take control whenever the feature requests for it. With safety concerns in a tight parking space because the car would be maneuvering in tight, narrow spaces, it's still a very slow and time-consuming process. As many of these features use ultrasonics, they are not able to detect lane lines and again rely on adjacent vehicles or some obstacle to detect a parking spot. The automated feature, the parking feature, can be broken down into 3 major sections: environment modeling and parking spot identification, which processes sensor information and gives a surround view around the traffic. Trajectory planning, which indicates a collision-free trajectory. And once we have this path, the path tracking control will generate the necessary braking commands, steering, throttle and brake commands to follow the path closely. For environment modeling, the first step would be to localize the vehicle in with respect to the environment. With respect to the environment, there are 2 major methods for this. The structural localization is where the system already has information about the environment. So, for example, with offline maps, it already has information about where the parking spot is going to be, um, with smart infrastructure or with communication, before it enters the parking spot, it might have information about the number of empty parking spots in that area. The second method is a completely exploratory method, which relies on onboard sensors to onboard sensors, plan techniques, aggregated localization mapping techniques to identify what's around the car and create an online map per se to perceive the environment. The next major consideration would be sample collection and fusion. Sample collection is based on a trade-off between accuracy and reliability and cost. In the parking process, in the parking feature, we would want the feature to be quick and accurate. These are a couple of sensors which are commonly used. Ultrasonics are effective for collision avoidance and work well with low speed maneuvering, but then the parking accuracy is also pretty low with just ultrasonic sensors. Cameras provide detailed information about the environment. It also recognizes parking lights, but again, the performance decreases in low light conditions. LiDAR and radars address this, overcome these disadvantages and have higher range and accuracy than ultrasonic sensors, and they are independent of light conditions, but LiDARs are more on the expensive side, and with radars, they may struggle with detecting a static object or differentiating between a static and a moving object. This module needs to account for all the parking configurations. The most commonly key parking configurations are parallel parking, perpendicular parking, and angular parking. And once the objects are detected, the system needs to start evaluating the potential candidates that it has for parking. The important few of the important aspects would be to determine the parking spot type in real time. Once we have the perception around the car, what type of parking spot is available. We also need to detect parking spot lines. Once that is done, if the system needs to verify if it meets the minimum criteria for width and depth, so that the car can fit in that spot. And finally, it needs to verify if the candidate is also a designated parking spot. Before I jump into trajectory planning, I would want to take a step back and also discuss what, based on the level of autonomy that the feature has, how can the feature be classified. So a semi-autonomous path assist system would be a level 3, SA level 3 feature where the driver is still in control. This graph shows how a typical parking process would look like. So the feature is activated by the driver, and the perception system would kick in, and the search phase would start while the driver is navigating through the parking lot. Then once a spot is detected, the feature requests for confirmation from the driver, and if it's accepted by the driver, the parking phase would start. If not, it would go back to the search phase and start looking for any parking spot. For automated valet parking system, the driver would park the car in a drop-off spot, get out of the car, activate the feature, after which the car is fully autonomous. It would navigate through the parking lot, find a spot, and park the car. And once the driver is ready to leave, again the feature is activated, and the car should return to a pickup location. So based on this, the trajectory planning problem can be divided into two aspects: the global path planning problem and the local path planning problem. The global path planning problem would be where the car needs to navigate from the drop-off location to the parking spot and to the parking spot to the pickup location. Whereas the local path planning problem is the parking maneuver itself. Once the spot is detected, from that to getting a car parked in the spot properly. For this research, we are focusing majorly on the local path planning problem, and we are trying to solve it as an inverse kinematic problem. Some of the challenges that we foresee are at the environment. As it's a narrow space and a tight environment, it's the probability of collision is higher. We also need to consider for kinematic constraints and data constraints as well. And we also need to identify the optimal start location so that the path planning problem becomes a lot simpler and easier if the start position is right. This research is still in the literary phase, and we are exploring what other researchers have done in this field. Some of the local planning approaches are like graphics algorithms, sampling algorithms to reinforcement learning and classification. Once a path is generated, the path tracking controller will make sure that it conforms to that path and the necessary linking commands are provided. The key considerations for developing this controller would be to account for bidirectional motion. So for the parking process, we are moving forward and reverse directions frequently. So it needs to account for that. The sensors come with a default noise. So the controller needs to be robust to the sensor noise. And again, handling all the moving constraints that the controller should be able to provide steering, accelerator, and take commands. Some of the path tracking controllers that we see in the literature are as well as scaling controllers and too complex for the logic so this research is a part of the EcoPark EV challenge, and we are working on the variability catalytic. The stock car did come with an automated parking feature, which was a level 3 feature, and it used 12 ultrasonic sensors, 6 in the front and 6 in the rear on the rear bumper. It enabled parallel and perpendicular parking configurations. And during our baseline evaluations, we tested the car for different test cases and scenarios. The average parking time was about 60 to 75 seconds, which was pretty high in our opinion. Now, for the test car, we are using 4 LiDARs as a sensor. 2 are mounted on the side view mirrors, 1 in the front and 1 in the rear, which provides us with a 360 view. As for technical specifications, we are looking at similar feature. We are looking at level 3 automated feature with parallel and perpendicular parking options. Some work that we have done until now that's relevant is as a team is that the LiDARs are integrated on the vehicle, and we are in the process of developing the calibration strategy to get us around the. We have good understanding of the perception system of the car and sensitivity strategies for other level 2 features that we are developing. The gas controller is a D-Space Cordera, which is integrated in the car, and we have a development tool chain set up for it. One of the key elements is interfacing the controller with the GM systems to provide names commands, which has been done. So the major objective of this research is going to be to explore ways of coupling sensor fusion and understanding automated maneuvers to test and implement the automated parking feature on the vehicle.
So the opportunity to actually do some of these things on an actual car of the EcoCar is really great. Perfect timing, and we have time for 1 or 2 quick questions from the audience. Yes.
In slide 13, could you explain the visualization of the that's good.
Yes. So all LiDARs have a 360-degree view, and because it's mounted in such a way, one is in front. So based on that, we are trying to stitch all the LiDARs together so that we have a surround 360 vision, and none of the detections are.
So this middle visualization is 3 LiDArs.
It's 4 LiDArs.
4 LiDArs.
How many papers have you assembled so far in your literature review?
Around 67.
So we've we're in this phase where we are looking at the literature to understand where the opportunities are to do some PhD dissertation work. And I think there's quite a bit of work possible. Sensor fusion ideas are important. There's an inverse kinematic problem that needs to be solved. So how do you develop the controls? A lot of cool stuff. No more questions? Let's thank Pooja again. And I think Mandana is up next. Can you hear me, Mandana?
Yes, I hear you, Giorgio. How are you?
Very well. So I'll do a very brief introduction and I'll turn it over to you. So Mandana Shuri is Associate Director of Licensing in our Technology Commercialization Office, which is broadly speaking part of our Enterprise for Research, Innovation, and Knowledge. Mandana knows CAR well. She pretty regularly attends our advisory board meetings, and she's going to talk us a little bit about technology commercialization. So I'll turn it over to you, Mandana. Thank you.
Sure, thank you very much. Thank you for having me, and thank you, Pooja, for advancing the slides for me. So if you go to the next slide. Okay, so as Giorgio mentioned, I'm the Associate Director for Licensing the Technology Commercialization Office. And when we are talking about the technology commercialization, everything will start with the invention disclosures that we have received from the faculty, research staff, grad student, postdoc, whoever that is doing something novel and very innovative inside the university. So here, I'm just giving you a very brief stats on where we are at this moment and where CAR is in that. So first of all, before going through these numbers, I have to mention that since CAR is an entity that has multiple affiliation with different units and departments, it was a little difficult for me to figure out what are the right number related to the CAR innovation activities, but I ended up that so the major department affiliation is mechanical and aerospace engineering, and so I went through that list. So last year, fiscal year 24, we got a total of 409 invention disclosure from the whole OSU, which 137 belong to the College of Engineering, which is a great number, a great percentage. And out of these 137, we received 24 from the Department of the Mechanical and Aerospace Engineering. And interestingly, 4 invention disclosure came directly from CAR, which the innovator mentioned the primary unit as CAR rather than any other department. So that's about that. That's why you see in that parenthesis I have the number 4. And this fiscal year so far, we got 212 invention disclosure from the whole university, and 112 come from College of Engineering, which is almost 50% of that, maybe a little more. Okay, so that's a great number. It seems that our College of Engineering is generating innovative stuff as always, but with a higher rate this year. And from this 112, we have just 11 from mechanical and aerospace engineering and 1 dedicated to CAR as of end of the February. So we are a little behind this year in terms of the departmental invention disclosure, but hopefully we will get to the trend by the end of the fiscal year, or maybe we have to think about why it's happening this year compared to last year. And we received last year about 91 issued US patent, which 42 came from the College of Engineering and 13 from the Mechanical and Aerospace Engineering. And last year, we executed 45 deals through the Ohio State, and out of those 45, 12 from the College of Engineering and 3 from the Mechanical and Aerospace Engineering. So I am not allowed to disclose the names in any type of public kind of event, but privately, if you want information, I can have the discussion with you people in so kind of the one-on-one meeting and give you the names or numbers or whatever that you want. But these are the information that I could just publicly disclose to you. So next, please. Okay, so a little bit about the innovation and commercialization process for those who are pretty much new to this space. And so everything starts from the innovation, from the university research. So number one shows you do the research, you do the great work, and then you figure out that there is something very novel and interesting, and you disclose it to your office. So invention and commercialization office receives your invention disclosure, and then we do two things in parallel, step 3 and step 4. Step 3 is the protecting your IP by filing a patent application or doing registering a copyright or trademark or trade secret based on what is your need. And university will pay all the expenses for everything. For example, for the patent, getting a issued patent in United States, usually it takes $15,000 to $20,000 to get an issued patent, and university pays for it. And if it's more than, if we file it in different countries, and again, the expense goes higher and higher based on where we are filing our patents. Sometimes we see the market all around the world. We file the patent all around the world because we want to make sure that we protect our patents and technology everywhere. And while the patent prosecution is moving forward, we do in our office, we do the marketing to make sure that we can find the right market and right commercial avenue for the invention that you have done in your lab. So it sometimes happens that we license your technology directly to an existing company or entity that is there. Sometimes we form a startup company to commercialize your technology. Either way, we need to execute a license. So if you form a startup company out of your invention disclosure, then we give more. Sorry, what did you say?
No, go ahead. That was just background noise. All good.
Oh, okay. Okay, sorry. So, yeah, great. So we execute license agreement, and if we form a startup company, we have a favorable points or terms for our startups. For example, we waive the license fee, we waive minimum annual royalty fee, we waive the past patent expense, not waive, we schedule the past patent expenses. So we are the terms that are very favorable to our startup companies. And then we get to the point that we commercialize the technology, and then we will make the impact through the direct licensing or startup formation. So I mentioned that everything starts from the invention disclosure that you submit to our office. So when you submit invention disclosure to our office, what you expect from us to receive from us? We have a process in place from the day that you submit invention to our office, and I call it non-urgent filing process. Why non-urgent? Because this process that you see, it takes 60 days from day 0 that a licensing officer, LO means licensing officer, is assigned to your IDF to the time that we make a decision to file a patent application or not. And during these 60 days, we always look for your feedback. So this is for the non-urgent filing process. We receive invention disclosure, we get in touch with you within 4 days, and within 14 days, we do complete our IDF evaluation. It means we look for patent search, prior art to see what's there, close or very similar to your invention, or maybe there is nothing similar to your invention. And then we schedule a call or a meeting or an in-person meeting with you to talk about it, and then we decide if we want to file a patent application or not. However, if there is an urgency, what do we mean by urgency? Sometimes you guys, you just call us and say, hey, I'm gonna disclose this tomorrow, or I'm gonna go to a meeting or a seminar or submit a NSF proposal or DOE proposal, and I want this to be protected before I do that disclosure, public disclosure. So we call them urgent filing process, which we don't go through all these 60 days. It just comes, you call us or you email us and say, this is urgent. We file it right away. We don't care about anything else. We don't care about the complete evaluation or any type of discussion. We just have a very quick discussion with you to see what is the urgency. Then we file your invention disclosure for a provisional application. And next one. Okay, so I talk about the process, everything. So right now I want to quickly touch base on the federal funding requirement. So you know that these days everyone is talking about the cutting federal funding and the problems that are with the grants, everything is on hold. Not everything, most of the things are on hold regarding the federal grant. So one important thing that we at the university should be careful about it is the something that they call it interagency Edison system, which is mandate us in university to report any invention disclosure that are coming from your federal grants. Okay, so if it doesn't matter, it's a copyright, is a software, is a whatever that you can call it, intellectual property is not just invention, is not just a hardware or a software, whatever that you can call it in intellectual property, we have the obligation to report it to the government. And if we don't do that, these are the consequences for non-compliance with that. Federal research funding can be withheld. Potential future funding implication. Government can take title to the university subject invention at any time following non-compliance. Grant closeout problem, administrative enforcement. All these problems are coming from the federal government if we don't comply with disclosing the intellectual property coming from your federal funded research. Please make sure when you are working through your final report and closeout process with the Office of Sponsored Research, you make sure that you disclose your intellectual property to us, then we can report it to the government. So this is the invention submission portal. You are all familiar, but so you can use this and go over there and submit your intellectual property as invention disclosure. And please don't hesitate to call me or my colleagues if you have any questions, and we can help you with that. Next slide, please. Okay, so we talk about, I want to introduce you one more thing that I think is important for you guys to know is, when I say guys, I mean everyone, it's just that. So it's the new software startup license model. So we simplified our software startup license because we figure out that most of the time the faculty and research staff, they do some type of consulting work, or they have their side company that they use the know-how and they use their technical expertise, that they obtain this expertise through their work with the Ohio State University. So they are not using directly Ohio State University resources for that, but they are using it indirectly. So we came up with many other universities around the nation that they have this model to protect their faculty and staff. If they are going to do any type of side business with their software or copyrighted materials. So this is proposing a three-model startup model. The first one is that you have a technology that is somehow relevant or a software that is somehow relevant to your knowledge knowledge and work at the Ohio State University, but is not directly using or using support of Ohio State, not related to any grant, I mean, current grant or previous grant or funding or facility or anything. So you come to us and you say, okay, I have this site entity that I work with that, but is not directly relevant to Ohio State, my Ohio State research. Then we execute a license with your company or LLC or Inc., whatever you have, which has zero of everything. Just the only thing is that you dedicate 1% equity of your company to Ohio State just to be protected by Ohio State. No one can sue you from Ohio State later and say you are using the resources from Ohio State or you are using your knowledge from Ohio State and have your side business. We've already resolved any problem with the conflict of interest office. They are familiar with this model and they approve this model. That's why you are allowed to be the signatory of this license agreement. If you are familiar with our license process, you know that we are not negotiating with our PIs. But for this specific model, the model 1%, and second model 4%, we are allowed to not negotiate, this is a pre-negotiated. So the PI is allowed to sign the license agreement on behalf of himself or herself. So the second model, startup model, is when you are using your knowledge that you obtained and developed at Ohio State University lab through the funding and other resources. Okay, so that's directly relevant to your work at the Ohio State. But when you are doing your side business as a consultant or advisor, you don't use university computer or lab or anything. You just use your knowledge and you'll use it in your own time. You don't use university time, anything. Then you pay 4% of equity to university and no other fees. These are this very experienced software startup that we put together. And the third one is our normal or regular software startup that you have a patent right, and so that covers inventions. Then that goes through our regular negotiation. So I really wanted to make you all familiar with this model as well, because I started working with a couple of you guys in CAR that they have such type of businesses and they are exploring the mechanism how they can protect themselves and their business while they have a license, and so no problem will happen for them when they are doing those side business or project through their own LLC or C Corp. Next, please. So I just wanted to again thank you all for giving me this opportunity to be here and briefly go through what's important these days in our technology transfer and commercialization world. So if you have any question or concern, please reach out to me or my colleagues, and Ryan Zinn, Devinder Randhawa, and I'm here always to respond to your questions. And let us know what are your expectations, what are you thinking, and how we can help you. And please submit your invention disclosure, federally funded or non-federally funded or sponsored by industry, whatever, to us, and we will be reaching out to you guys to work through the process. So I am done with my slides, but if you have any questions and concern, I will be happy to respond.
Thank you, Mandana, very kind of you. And quick question or two?
Excuse me, I
Yeah.
don't hear you, sorry.
Oh,
Can I talk like this, or do I have to come there?
can you hear Mandana?
Can you hear?
Yes.
Yeah. Again, my name is Rama Yadavalli. I do remember we had a meeting long back with Ryan Zinn and yourself. I don't know whether you remember me. Anyway,
yes.
the last slide was very interesting to me. And now I'm an emeritus professor here. Yeah, that one. So the first, second column, after license. So I want to talk to you in person or maybe with Ryan also there about some of the progress I have made in some kind of a software development. So I'm so glad that I was here at the right time, I think. So I did not know about this so-called licensing model. So all I just want to say is that one of these days I'll give you an email and I would love to talk to you.
Yes, perfect. Yeah, I look forward for that, and yeah, I will be happy to schedule a call with you and talk to you. So one thing that yeah, Rama, that was your question, right?
Right.
Okay, perfect. Yeah, I look forward to receiving your email. And one more thing, unfortunately, I'm not able to be there in person. I changed my work schedule to fully
Right.
remote working, but
Okay.
I'm always available to have a Teams or Zoom call, and so I'm available.
That should be fine. Yeah, thanks.
Yeah.
Thank you, Rama. Thank you so much, Mandana, again. And I just one last comment. Most of the people in the audience are graduate students, not everyone, but most. And I think that it is a very good thing to prepare invention disclosures as a result of your work. Speak to your PI advisor every time you think you have a question about whether this is a subject that could be appropriate for an invention disclosure. And we'll clarify further. And as you have heard, Mandana is available to give further clarification at any time. Thank you again, Mandana.
Sure.
The timing was perfect because
Great.
now we're ready for part
Thank you.
3. And part 3 is a presentation given by Rebecca Quintana, who is a PhD student. Rebecca is also passed her qualifying exam and working on her dissertation ideas. And she's, I think, pretty far along on some of that good work we're doing. We're doing some work on topics that are related to batteries, at the moment sponsored by the Ford Motor Company. But Rebecca has extracted some more fundamental ideas out of this. She will share.
Good evening, everyone. I'm Rebecca Quintana, a student of Dr. Izumi. Today I'll be talking to you all about the degree of observability of lithium-ion batteries for electrified vehicles. So during the course of my presentation today, I will just give a quick overview of observability, the types of observability, then introduce you guys to the degree of observability, DOO, and mention something called observability, and then enlighten you guys about some criteria for degree of observability analysis. Then I will close with the simplified case study to show you how degree of observability applications can be applied for like the lithium-ion batteries. So I'm pretty sure most of us in the room know about observability. So observability is a fundamental concept in control theory and system analysis, which shows us or talks about the ability to reconstruct your system state coming from your measured inputs and outputs. Generally, you can see there are two types of observability. We have structural observability and then the common ground observability. So what exactly is structural observability? That might be a part that we're not all familiar with. However, structural observability, which is the ability to reconstruct your system state, but this is based only on the system structure, in the sense that you're not taking into account the numerical values of your system's parameters. You just look or you check your system's observability based on the system's topology. A way to check for structural observability, like using the bipartite graph matching, which is shown in the figure on the left. Yes. So you have equations E1 to 6, E6, and you have the variables in the circle. And you want to make sure that you do have a complete matching from each circle through equations from the measured outputs to all your state variables. Once you have a complete matching, that means the system is structurally observable, which of course means that you need to have at least a just determined system. Now, common rank observability is the one most of us are familiar with, where it's used in linear systems theory. For instance, you have an LTI system, linear time invariant system, where at the time here we have, our A, B, C, and D matrices. For the common rank observability, we need to check if a system is common rank observable, then we need to build or construct or compute something called the observability matrix, which is computed in this method. You have your C matrix and your A matrix to build that. And you check to see if this observability matrix O is full rank. If it is full rank, it means that your system is common rank observable. Another thing I would just point through in here is the observability gradient, which is defined this way. You can just look at it as being an approximate of the observability transpose observability. You can also check to see if the rank of the observability matrix of the observability gradient is full. So the observability matrix and the observability gradient tell you the same thing about the extent observability. So common rank observability, you just check the rank of either the observability gradient or the observability. So now degree of observability. This is now a concept that's not as popular, but of course we are getting to know about it today. Degree of observability tells you how well your state variable can be observed or inferred from your output measurements. So the previous types of observability I just discussed, the structural and the common rank observability, they give you a binary answer to the observability question. Yes or no, is my system observable? However, the degree of observability gives you more of a quantitative measure on how observable your system is. So it's usually useful when you're trying to analyze systems where some of the state variables cannot be directly measured, but then you need to have an idea of what these states. So now back to the observability diagram I had previously mentioned. For degree of observability analysis, the observability gradient is mainly used for this. The observability gradient considers all state variables together and their influence on the outputs based on the system dynamics and outputs. So, like I had mentioned previously, this is how the observability gradient is defined mathematically. And you can see, of course, you have your state transition matrix involved and your output matrix D involved, defining your observability gradient. So, of course, you have system dynamics, output matrices, and all your state variables in your observability gradient, which I've also mentioned is approximately equal to or the same as the observability matrix transpose observability matrix OT. Yeah. So this yields the observability gradient is a symmetric matrix, positive summary definite or positive definitive. And because it is symmetric and positive definite, you can make use of eigenstructure analysis, which leads us to singular values. So the energy of the LTI, the linear time invariant systems measured output, is directly related to the singular values of your observability gradient, which is why in literature today, some of the criteria that is used for degree of observability analysis make use of the singular values of your observability gradient. So, for instance, some of them that I have listed out here include the spectral radius, which of course looks at the maximum, the largest singular value of your observability gradient. That tells you or gives you the maximum energy / information that you can get from your system output. The trace, which is the sum of all your singular values, tells you the total energy that you can from your system output. However, the linear singularity criterion just focuses on the smallest singular value of your observability gradient. So that just tells you, okay, this is the smallest amount of energy information you can get from your system outputs, it tells you how close your system is to being unobservable. The condition number takes into consideration the largest and the smallest singular values. So therefore, it takes into consideration or shows you the maximum and minimum energy information. While the determinant, which is like overall system observability, tells you, okay, if my determinant is 0, it means that I have some unobservable states in my system. While if my determinant is high, then of course I have great observability in the system. One thing I would also like to point out here is that the observability grammar it doesn't tell you exactly which of the states is most or least observable because it is a linear combination of all your states. So what it can tell you is that the eigenvector direction, this is the this is the most observable eigenvector direction to get the most observable direction where you can get most information about your system's observability. So it's a combination of states, of system states, not just each of the states. So application of DO, degree of observability. Some of the major applications for LBI/electrified vehicles includes optimal sensor placement and optimal sensor selection. Why we have, for instance, we have electric vehicles that make use of battery packs that consist of hundreds of cells, right, in the battery pack. Due to geometry, the battery geometry, financial and computational power constraints, we can't afford to have sensors on every cell, right? If we're trying to measure various cell properties. So at the end of the day, we can only have a limited amount of sensors. But then it's trying to, using the DO analysis, it kind of like helps us to be able to get the maximum system observability with the limited amount of sensors we have. So I will give a simplified case study, very simple case study of how we can make use of DOO analysis in order to choose like an optimal sensor. This is just a simplified case, please. So here I have a case where I'm trying to decide if I want to use a temperature sensor or a heat loss sensor to measure or to get information of temperature information about two cells that are connected by a tab with a pin in between foams at the extreme end with the pin sitting on a cooling plate. So which of the sensor temperature and heat loss sensors will give me the maximum, the most observability that information? So I use the traditional observability criteria, which is, like I mentioned, a yes or no question or answer to my question. And as you can see in the table on your right here, you can see, yes, it tells me that using either sensors, my system is going to be observable. But this doesn't tell me, okay, which of the sensors will be better use for me, or will be a better use for me. So I go on to try to apply the DOO analysis to that. And I decide to choose two criteria. The first one is the condition number. So which like I had mentioned before, I take the maximum singular value and the minimum singular value to compute the condition number of my system. And then the best system observability is the one that has the smallest condition number. So from the result, it showed me that a heat loss sensor would be best or better in that sort of scenario for that sort of battery configuration. I do the same for the near singularity criterion, in which I'm just trying to see, okay, how close is my system or are the two systems to being observable? And the one that's going to give me the best system observability would be the one with the highest near singularity value, which means that that is the one that's as far away from being unobservable compared to the others. And same here also, I guess the K plus to be a better option. So just to conclude what I have told you today or introduce you to, I have mentioned that a system is observable if it's possible to reconstruct the system states from your measured output and inputs. The traditional observability that we're most common with is, or that is most common, is an answer, is a yes or no answer to the observability question. However, DOO, degree of observability, answers the how observable question, and it can be used for sensor placement, sensor location. So yeah, that's what I have.
Thank you, Rebecca. Nicely done. Everyone has been a wizard with being on time today, so we still have some time for questions.
Yes.
Yes.
Okay. I'd like to ask, do you, when you have a large battery pack, do you solve this as a combinatorial problem and determine which positions are the best using this theory? Is that what's the purpose of this?
So that is one of the things I'm trying to figure out for my dissertation. I'm going to apply this analysis to large battery packs. See how, yeah.
It's a good question
Yeah.
that you're asking and sort of pointing in the right direction, but it's not that simple.
I can understand.
You can see why. I mean, it's a very large system.
I mean, even if you brute force it, there are so many combinations that it's
Yeah.
not possible. It's not practicable. So
We're trying to be more clever than that.
yeah, I believe, yeah, that's what I figure.
Good question.
Thank you. Thank you. Very interesting.
Yes, Professor.
I just came here for this particular presentation. When I came here, I thought, how come I'm seeing something else here? I came here for this particular presentation.
You want-
So it was not there yet.
Yeah.
Very interesting. And yeah, I kind of, I've been in this control theory for a long time to keep asking a lot of questions. But one thing I want to go back to second slide or something you said, I'm interested in that part. Structural observability, structural controllability, that kind of thing where, as you said, it has no connection to the numerical aspect of it. I like that. And in a way, some of my new research, which maybe Dr. Rizzoni also knows a little bit, but again, it's very new here. But that kind of idea is what is going on in everybody's mind, to dissociate observability or controllability or any linear system properties to the numerical issues. And instead, in my research, research inspired by qualitative methods. Structural observability question that you ask is something very similar to qualitative stability. That means without knowing any magnitude information, what is the qualitatively, how good is it, how good observable? So that leads me to, kind of used to being in the quantitative world for so long. We are simply used to always dealing with numbers. The moment something is qualitative, we don't have that much of knowledge about it. But just want to let you know, maybe I will get a chance to talk to you later on. Qualitative stability is a separate area in ecology. That's where I learned a lot of new concepts. Going back to our application part here, not the second slide. I want to understand from you, maybe not this one, computation. Where did you say? They are very first one.
So the very first
The very first one, that means where you said computation and then how it is related to battery. Right, yeah, right. The last tick mark there. Financial and computational power constraints.
Yeah.
That is the one I want to understand from you guys, application people. Suppose I give you an algorithm inspired by, let us say, that structural or qualitative. I will give you an algorithm where the computation is extremely simple. No Riccati equation, no Lyapunov equation, nothing. Simple algebraic operations on the elements of the matrix. I'm wondering, again, I want to know from you, does that help us that if we use that kind of a computationally kind of a savings type of algorithm, will it increase the battery life a little longer? I'm curious. So how does computation of our control algorithms, what effect will they have on the battery life? That's what I want to understand. If there is some correction there, which I want to see, then I can give you a simple control algorithm where hopefully it will increase our battery life. Hopefully, that's all the hope. And that's why I want to collaborate with you guys to use some of these new ideas. They're too extreme than this one, like no magnitudes, but still it will give an answer to, yeah, if I somehow, as engineers, we still have to have a computation algorithm. But the difference of algorithm is very simple calculations plus and just algebraic operations, not solving the differential equation. Yeah. That makes a difference. Yeah. In other words, eigenvalues are, if you give a dollar value to eigenvalue computation, it is extremely expensive.
Yeah.
Extremely expensive. Suppose I give you an algorithm without eigenvalue use at all. Simple A11 plus A22 by 2. Some kind of a small algebraic operation. Yes. I believe that I gave a seminar at Berkeley, and they said, yeah, there should be a connection between battery life. Scott Maurer was interested in what I said. Yeah, that sounds like a good thing.
We'd be very happy.
Right. We should collaborate and we should.
Let me ask the advisor question. Go
Right.
back to your structural observability.
Right.
Tell us, please, when is structural observability equivalent to Kalman rank observability? This is like a candidacy exam. Okay. What must happen so that when you say that a system is structurally observable, it is also Kalman rank observable?
So it's something I'm still trying to figure out how the two kind of like really relate. But one of the things I'm sure of is that even if your system is Kalman rank observable, then it is definitely structurally observable.
Okay.
However, because the Kalman rank observability includes numerical aspects to it, so it's giving you more of like a definite aspect. However, the structural observability doesn't take into account the value, the parameters, and everything. So therefore, it's giving you the best case scenario that you can have for the system observability, because the structural observability, when you take a look at it, there are things that, well, I don't want to go too deep, but then there are things we call non-zeros and real zeros. So the structural observability kind of like non-fixed zeros. The structural observability only shows you where you have your fixed zeros, which affects if you, for instance, build your observability matrix just using values, variables, right? You don't put numbers to it. Then okay, you can have some variables to be zeros, which can then affect if your, for instance, your observability matrix is going to be full round or not. However, with the Kalman rank observability, you know what is a zero and what is not a zero. While the structural observability just tells you, okay, you can have a zero here, you can have a non-zero value here. So of course, it will just give you the best case scenario of the system observability.
So it's not immediately obvious because, as Rebecca said, Kalman observability implies structural observability, but the converse is not necessarily true. And she also said correctly that she's working on formalizing some of these proofs. But the point that you made, I mean, you can use symbolic mathematics to determine whether the observability matrix of a system is full rank or not. But you could run into the situation where some parameter value brings something to zero, then you may use observability. Well done. Thank you, Rebecca. Thank you, everyone, for coming. I am running off. Thank you for being on time. Really appreciate it.